Here in April, their meeting, but it's not a very good time to have a good talk. I'm very happy when this opportunity invited me to give a talk now. Here we're talking Glasgow on Monday. The tour of Scotland, seeing us, best weather in autumn. Today is actually quite good. Okay, Oscar will talk about stable moduli spaces of high-dimensional manifolds.
Yes.
Close to my heart.
Well, thank you very much for letting me speak here. So let me write up what I'm talking about first. And many words in the title will maybe be a little mysterious, but I'll introduce all of these. So stable moduli spaces of high-dimensional manifolds, and this is all joint work with my collaborator, Soren Galatius. So first, let me explain. So high-dimensional manifolds, hopefully, is familiar. Let me explain what I mean by moduli space of manifolds first, because this is not a generally used term. So let M be a smooth, compact, d-dimensional manifold. And then I want to define, in fact, let me call it W. And then I want to define what I'll call M of W, which is meant to be the moduli space of manifolds diffeomorphic to W. And the problem is, of course, that smooth manifolds don't have moduli in any meaningful sense. You cannot deform a smooth manifold to a nearby smooth manifold. You're either diffeomorphic to W or you're not diffeomorphic to W. So naively speaking, this space ought to be maybe 1 point or something like that. But the point is that manifolds do, however, have automorphisms. So in fact, the space should be even less than 1 point. It should be 1 point divided out by the diffeomorphism group of the manifold. So what we have to do is make sense of that. And what I want to do is the following. I want to take, let me first define a decorated version. I want to take the space of embeddings of my manifold W into n-dimensional Euclidean space. And for this part, let me suppose that the manifold W is closed. I'll tell you how to deal with the case of manifolds with boundary in a moment. And now on this space, the diffeomorphism group of W operates by precomposing an embedding with a diffeomorphism, and then you get a new embedding. And I can divide out by the diffeomorphism group of W. Okay? And I've already said, before I divide it out, I already said this space. So as a set, hopefully, you know what I mean. I mean all the set of smooth embeddings of W into Euclidean space. But I want to topologize it. And because the manifold W is compact, there's basically one way, meaningfully, to topologize that space, to use the Whitney topology. And I don't need to add adjectives because the manifold's compact and the two possible Whitney topologies agree in that case. Similarly, I want to topologize the diffeomorphism group with the Whitney topology, and if you do that, it acts continuously on this space, and so I get a topology on this quotient space. So this is my first definition, and somehow it's a little unnatural because I've fixed this dimension of the Euclidean space, and that's not really relevant to what I'm studying. So I notice that there are canonical inclusions between these by including Rn into Rn plus 1 as the first n coordinates, where 0 in the last coordinate. And I define MW to be the union of these under these inclusions. With the topology, with the colimit topology as well. Okay, and this is what I claim to you is moduli is a possible definition of the moduli space of manifolds of the type W. What is some justification for that? Well, the space of embeddings of W into R infinity, which now that means the obvious direct limit of the embeddings into Rn, is I'm going to say is contractible, more precisely is weakly contractible, basically by Whitney's embedding theorem. Okay, so the baby version of Whitney's embedding theorem says that if you have a manifold, it embeds into some Euclidean space. A slightly fancier version says, furthermore, if you make the Euclidean space a bit bigger, then any two embeddings become isotopic. And an even fancier version says if you make it even bigger, then any two isotopies become isotopic, and so on all the way up. That's basically talking about homotopy groups of the embedding space, and if you take R infinity, then all the homotopy groups are 0. So this means weakly contractible. i.e. all the homotopy groups are 0. And so that's one point. And the second point is that the diffeomorphism group of W acts freely on the space of embeddings. Why is that? Well, if it fixed some embedding, embeddings are in particular injective maps, right? So if you fix an embedding, then you fix every point on W, but that means you're the identity map, right? So it acts freely on this space, and this space is contractible, or at least when in its infinity the space is contractible. And that means what I've defined here is a model for the classifying space of the diffeomorphism group. Because that's the recipe for constructing the classifying space of a group, right? You find some contractible space on which the group acts freely, and you take the quotient space. The point is here I have so normally the classifying space of a group is not really a meaningful concept. The best you can say is that various models for classifying space of a group. And what I've taken here is a particular point set model that's very easy to think about, or at least it is for me. And this is also justification for why one should think of this as being a moduli space of manifolds, because so in algebraic geometry, where the term moduli space comes from, there are two properties you want it to have, really. You'd like each point of the space to correspond somehow to one of the objects you're talking about. In our case, a point in this space, I'm afraid I just erased it, but a point in this space is a subset of R infinity, which is diffeomorphic to W. It doesn't have a diffeomorphism to W because we quotiented out by reparameterizing it. And the second property you'd like it to have is that it classifies families in the correct way, of families of whatever object we're talking about. And that's true here as well. If I take the set of homotopy classes of maps from X into my space, here X is some reasonable space. So maybe a manifold or something. In fact, it does need to be power compact. Then this is naturally in bijection with the set of fiber bundles pi from E to X, a smooth fiber bundle with fiber, the manifold we're interested in. And just as here we've quotiented out by the relation of homotopy, so here we've quotiented out by the relation of bundle isomorphism. And it's exactly the same as when you use Grassmannians to study vector bundles, right? Everything I've done is completely analogous to what you do there. First you look at d-dimensional subspaces of Rn, and then you let n get bigger and bigger until you look at d-dimensional subspaces of R infinity, and then you get exactly the same sort of bijection between homotopy classes of maps and vector bundles modulo bundle isomorphism. So it's entirely analogous to what you do for vector bundles. Similarly, cohomology of this space, just like the cohomology of Grassmannians is characteristic classes of vector bundles, so the cohomology of this space is the ring of characteristic classes of such bundles. So let me just say such bundles. Okay. Let me quickly, as I promised, tell you what you do if the manifold has boundary. So if the boundary is not empty, I mean, it's entirely analogous, but I just have to. Let me just define the infinite version. You'll immediately see what the correct definition is for finite n. We take embeddings of W into R infinity cross 0 infinity, so into a sort of infinite half space. And we take embeddings that on the boundary of the manifold W have some fixed behavior. And so we fix an embedding of the boundary once and for all, and then we take embeddings of W into this space that on the boundary of W are the fixed embedding of boundary W into R infinity cross 0. Okay, so the picture is we have this. This is my R infinity. This is my half line. I fixed my embedding, or I guess this should be E of boundary W, in that space, and then I take the space of all extensions of that. So all ways of extending that to an embedding of the big manifold. Again, because there's so much space, there are extensions, and furthermore the space of extensions is contractible. And again, I do exactly the same thing. I divide that by the diffeomorphism group of W, but now you notice that if I allow all diffeomorphisms of W, it won't act on this space because it will change the embedding on the boundary. And so the best thing I can do is act by the diffeomorphisms, which are the identity on the boundary. So this is my definition if W happens to have boundary. And again, this is a model for the classifying space of the diffeomorphism group relative to the boundary. And there's a similar description of what maps into this space means. It's fiber bundles with fiber W, and a bit more data, which is on the boundary, you have a trivialization of the family of manifolds. Okay. So my goal is to understand something about the topology of this space MW. And to do so, I want to compare it with another space, which, to begin with, is going to sound more complicated, but I hope to convince you that it is in fact the sort of space that you can study easily by methods of homotopy theory and so on. And the reason it sounds more complicated is that here we fix the manifold W, whereas the space I'm going to describe now is about all d-dimensional manifolds. And I'm going to use a technique called scanning to construct a map from this space to this much more general sounding space. So let me write phi d of Rn, and it's going to be let me describe it as a set first. It's going to be the set of d-dimensional submanifolds of Rn. Okay? So it's the set of X inside Rn, satisfying two conditions. The first one is technical and not so important, which is that X is closed as a topological subspace. And the second one is that X is a d-dimensional smooth submanifold. Okay, so I take the set of all subsets of Euclidean space which are smooth d-dimensional submanifolds, and also are closed as a topological subspace. This is just to exclude things like spirals that accumulate onto themselves and stuff like that. Right, how's one meant to think about this? Well, maybe if we take n to be 3 and d to be 2, then we're talking about surfaces in three-dimensional space, and they're allowed to be non-compact. I didn't know say anything about that, so they can go off as far as you like this way, they can go off as far as you like in other directions. They can have plenty of components, and the components can maybe, you can have sequences of them going that way as well. They could be all sort of knotted inside each other if we're in some finite space. I won't draw that because I'll get it wrong. So it's all possible pictures like this, okay? So you realize this is quite a big set. And now I'd like to describe a topology on this set. Unfortunately, I can't give you a precise definition of it because this is rather long, but I'll try to describe for you what sort of things are continuous in the topology I want to talk about. And there's basically two basic properties we want the topology to have. One is that if I deform manifolds a little bit, I'd like to say that's close to the old manifold. If I deform the embedding a little bit. So one property I'd like to have is that maybe that's my one manifold in some Euclidean space, and maybe I take a section S, maybe I take a compactly supported section of the normal bundle. So we start with the manifold M, it's embedded, so it has a normal bundle, and we take a compactly supported section of the normal bundle. Then there's a path, or what I would call a path, from M to the section that just scales the manifold in the section direction. Right? So it just pushes it off like that. And I'd like to say that this gives a path starting at M and going to S of M, just by scaling the section. I'd like that to be a continuous path in this topology. So that's something I'm allowed to do. And I don't imagine anyone would have any objection about that. But the second thing I want to be allowed to do is a bit stranger, which is, suppose I have a sphere like that. I want to be able to move it to the right faster and faster, so that at time 1 it's at infinity, and the manifold I see is the empty manifold. And I want that to be a continuous path. Okay, I move this to the right, and I'd like this to be a path. I'd like this to converge to, notice here that the empty set is a manifold of any dimension, so the empty manifold is a point, and it's going to be a base point in this space. So if I take some maybe compact thing and I move it off to infinity, then that should converge to the empty manifold. And similarly, it doesn't just have to be a compact thing. If I do anything that sort of is eventually constant on any compact ball, then that should converge. And basically, there's a unique topology that mixes these two things. So if you want these things to be allowed, but also convergence to mean convergence on all compact sets, then you get the topology that I'm talking about. So for example, if I only allow these sort of things, then that's one manifold in R2, and that is another one. And if I only allow this sort of thing, however close I make that to that, it's not close in this topology, because there's not it never looks like a compactly supported section. Okay, but if convergence now means convergence on compact sets, then given any compact set, then there is a compactly supported section that looks like that. And on that compact set, that's indistinguishable from this section. So this is some, like I say, it's a bit painful to actually describe the topology, but this is the idea. So convergence is convergence on compact sets, and compactly supported deformations are continuous.
And why did you get to infinity at the empty set in finite time?
Well, I mean, you just move it like. So yeah, I take the path that sends a manifold to, I don't know.
No, I understand.
Translate it. Well.
Yeah, so why the emphasis on finite? I mean, could you not have asked that you converged, just like a vector field can go off? I mean, it's the finite you wanted in one or any finite time.
Right.
Why did it have to converge to that rather than going to the empty set as t goes to infinity?
But that's really just saying, I mean, that's just making the real line have extending it by infinity at the end, and that's homeomorphic to the compact interval. I mean, that's not really a different notion of convergence. You could say that, sure. Right, so you could say at time infinity it's the empty set, and then convergence is just the extended real line notion of convergence, sure. No, because if I okay, so if I take the manifold like that and I rotate it a bit, that's obviously far apart from the original manifold, but it's isometric to it, so it's equal in the Gromov-Hausdorff metric. So this sees the embedding, not just the abstract metric space. Okay. So inside this space of all d-dimensional manifolds, there's a subspace of the affine d-dimensional manifolds. So the ones that, well, let me just say, we have the affine d-manifolds. So here we have all of them, and that we think of the affine manifolds. What are they? They're translates of planes. So, well, first you have to give an affine manifold. What do you have to give? Well, you have to give. So let's translate it to 0, and then you get a d-dimensional subspace of Rn. So we get a point in the Grassmannian. But now we have to remember how to translate it back to wherever it was. And to remember that, you need to give a normal vector to that plane. So the space of affine d-manifolds is the total space of the orthogonal bundle to the tautological bundle over the Grassmannian. Right? So it's an affine manifold. You have to give a d-plane, and then you have to give a vector that tells you where to translate it to. So there's a map from. So putting this in brackets, I really mean the total space of this bundle. There's a map from that total space to my space of all d-manifolds that sends a plane to itself thought of as a manifold instead of thought of as a plane. But now, on any compact set, as I move away in the fiber direction in this bundle, i.e. as I translate the plane further and further away, it eventually intersects any compact set in the empty manifold. So this extends to the one-point compactification of this space by sending the one point that you add here to the empty manifold here. And the one-point compactification is, of course, the Thom space of this vector bundle. So let me write. And the extension is given by sending the one point we add to the empty manifold. Right? And because moving to infinity along the fibers means moving the plane further and further away from 0, that does converge to the empty manifold. So this is a continuous extension. And to convince you that this space is really not as, I mean, as a space it's very big and complicated, but as a homotopy type it's not so bad, because I claim this map is a homotopy equivalence. Let me just write that and then try to justify it a little for you. So I won't give you proof, but I'll give you the proof if we restrict to a certain subspace of these. So let's restrict to the subspace of manifolds that go through the origin. Okay, so this is, consider manifolds containing 0. Then on this side, that's just the Grassmannian inside the Thom space as the 0 section. So here we have the Grassmannian of 3 planes in Rn, and here, well, I don't have a name for it, so let me make up a piece of notation. Psi d Rn 0. So this is all d-dimensional manifolds in Rn that contain the origin. In particular, they're not empty. Now here we of course have a map going the other way. Right? We have the map that sends a manifold to its tangent space at 0. We know it goes through 0, so we can take its tangent space there. And now if we start here, think of it as a manifold, then take its tangent space, well, that's the identity. You haven't done anything by doing that. But if we go the other way, if we take a manifold, take its tangent space, and then think of its tangent space as being again a manifold, that clearly changes the manifold, or that changes the point you get in this space. So maybe we start with that manifold and we take its tangent space, and that gives us that affine manifold. But now I claim there's a canonical homotopy between them, and that's given by rescaling the Euclidean space more and more. So rescaling Rn and carrying W along with that rescaling gives a path from W to its tangent space in this topology, which I think is, I don't know, that seems pretty reasonable, right? That's kind of what we mean by the tangent space. It's infinitesimally what the manifold looks like, and scaling the Rn is the same as sort of just zooming in on the manifold, really. Scaling outwards, I mean, right, not inwards. So that gives a homotopy from the other composite back to the identity. And in general, manifolds don't go through the origin, and you need to play around with basically you look at the nearest point to the origin, and that gives you a normal vector, and you get a tangent. Then there's a bit of subtlety because there may not be a unique nearest point, but you can easily deal with that.
Do you know what we all many manifolds connected?
No.
No.
They're like the thing I drew, right? It can be anything. All it has to be is locally d-dimensional and closed as a subspace, so it doesn't accumulate. Okay. So now hopefully I've convinced you that this space, or even without the decoration, as a space, we have a nice point set description of it, but as a homotopy type, we also understand it very well. It's just a Thom space over a Grassmannian. You know, it's cohomology, you know, all sorts of that sort of thing. Now I want to define a comparison map between my original space of manifolds, M of W, and this space, or something related to this space. And I want to define it in the following way. So let me take a vector and one of my manifolds, and I want to produce a map from this to psi d of Rn. And the map is very easy. I take a vector v and a set x. X is now a compact subset, right? And I send it to x translated along the vector v. Okay. Now, again, what you notice, because x is compact, if I fix x and just think of this as being a function of v, then eventually it leaves every ball. As the norm of v gets very large, this eventually leaves every ball. So this again extends to the one-point compactification of Rn, which is the sphere. Where we send sort of infinity, comma, anything to the empty manifold. And now I want to just take the adjoint of this. Okay, so I want to think of this as a map from the space of manifolds to, well, let me write the space of maps from Sn to this. But you don't just get any maps, because you know that infinity always gets sent to the empty set. And infinity is a natural base point over here, and the empty set is the natural base point here, so you actually get base pointed maps. And now, because it's normal in homotopy theory, and I'll do it in a minute even if I don't try to, I'll write this as loops n phi d of Rn. So it's the n-fold loop space of the space psi d of Rn. Damn it. Of course, here I'm thinking of x as being a manifold in Rn, so I'm actually in this space. Okay, now both sides have a sort of have this dependence on n, and I said when I was talking about this sort of object that I really want to take the direct limit over letting n be bigger and bigger. Luckily I can do that on the right hand side as well, by the same sort of map. There's a sort of obvious stabilization map on that side that increases n by 1 as well. So taking limits, as n tends to infinity, I get a map from this space to the direct limit of these spaces on the right. And this sort of object is something very well studied in homotopy theory, and in particular in stable homotopy theory. It's what's called an infinite loop space. So it's a space which is an n-fold loop space for every n. So it's an arbitrarily high loop space, if you like. And that's basically the main object of study in stable homotopy theory, and there's many tools for calculating anything you might like about it. So my claim is that this side is well understood, even though it seems to be rather more complicated. Let me just write it a bit of a different way, using the lemma that I had here before to write this psi d as a Thom space. So this even looked more maybe difficult because it had this psi d space that I defined in, but this is something completely standard. Right? It's Grassmannians, Thom spaces, loop spaces, all very standard constructions in homotopy theory. Okay. So this is my main comparison map. This is what I'd like to use to deduce information about this space. Now, one very obvious problem is that this space depends on W, while this one, in a sense, is constructed from all d-dimensional manifolds. Okay, so we can't, for example, hope for this to be a homotopy equivalence, or something as naive as that. So you have to think about how, what's the least damage one can do to this space to make this be an equivalence. It'll never be a homotopy equivalence, but what I'm going to talk about is under what conditions it's a homology equivalence. So if you do the correct thing here, then this map induces an isomorphism on homology. And this is this way of viewing it is completely ahistorical, but let me phrase how some older results can be viewed as coming from this construction. So the first result I'd like to talk about is, or has been proved by many people, originally by Barrett and Priddy, later by Quillen, and by Siegel at about the same time. And it's basically, it's a discussion of this theorem, although that certainly wasn't used by these people, but this sort of scanning map is originally in the work of Graham Siegel, when the manifolds are zero-dimensional. Okay? So a compact zero-dimensional manifold is also known as a finite set, and the diffeomorphism group of a finite set is nothing but the symmetric group on that set. And the theorem... Question? No? And the theorem in that setting is as follows. You take, let's write Wn to be n points, and we look at MWn, and we think about what this thing over here is, okay? Now this was the Thom space of a certain bundle over the Grassmannian of D-planes in Rn. Now there's precisely one zero plane in Rn, which is 0, so the Grassmannian is 1 point in that case. The tautological bundle is the zero-dimensional bundle, so its orthogonal complement is the n-dimensional bundle over 1 point. So its Thom space is the n-dimensional sphere. So this side is the limit as n goes to infinity of loops n Sn. And in this case, it's very easy to see what this... I was a little vague when I said how one stabilizes with n earlier. In this case, it's very easy to see. If I have a map from Sn to Sn, which is what a point in here is, I can suspend it, and I get a map from Sn plus 1 to Sn plus 1. That's what the maps in this direct system are. In general, there are sort of obvious generalization of that. So what I've constructed so far gives a map this way, at least once you pick an inverse. I mean, the natural map went that way, right? So one has to pick a homotopy inverse to that, which isn't a very concrete thing to do, but let's ignore that for now. But now we can sort of stabilize on this side as well by adding an extra point to the configuration. We make the manifold bigger by adding a new point. So here we can take the direct limit as the number of points goes to infinity by adding a new point. And the theorem is that then if we do this, this map is a homology isomorphism. Meaning that when you take homology groups of both sides, this map induces an isomorphism. On the other hand, as I just mentioned, at the beginning, this moduli space was meant to be a model for the classifying space of the diffeomorphism group. Here, the diffeomorphism group is a symmetric group on n letters, so this is nothing but the classifying space of the symmetric group on n letters. And when we take the direct limit, well, that's what you might call the symmetric group of infinitely many symbols. But it's more precisely, it's the compactly supported permutations of infinitely many variables. Right, because there's a direct limit, an element in here you only ever see are finite permutations. So it's finite but arbitrarily large permutations. And this, again, is an ahistorical remark, but for example, the symmetric group is certainly a finite group. We agree that. So its rational homology is 0. That's true for any finite group. So the rational homology of the direct limit is the direct limit of the 0 group, so it's 0. So the rational homology of this side is 0. That, once you go through the motions of unraveling what that means over here, is equivalent to the statement that the stable homotopy groups of spheres are finite in every non-zero degree. Because this space, kind of by definition, its homotopy groups are the stable homotopy groups of spheres. So this is another way of proving this theorem due to Serre, that the stable homotopy groups of spheres are torsion in positive degrees. But again, it's very ahistorical. That's certainly not how one should prove it. Okay. The second theorem along this line that I'd like to talk about is due to Madsen and Weiss. Much more recently, these were sort of, I don't know, 71 or so originally, and this was maybe 2007, although it had been around maybe 5 years earlier than that, but it was published in 2007. And the theorem is when you let D be 2, so we're studying surfaces. So we let let me write SG1 be a surface of genus G with one boundary, i.e. the standard picture that one draws in such situations like this. And then you do exactly the same thing. We look at this space of surfaces of this topological type. Now this manifold has boundary, but I told you what this space should mean when the manifold has boundary. We fix a standard place to put its boundary and only take relative extensions of that. And then you have a space on this side, which is exactly the analog of the thing I wrote, with a small tweak. And let me just write the usual notation for it, and then I'll explain exactly what it means. This is exactly the same construction as this, where we take D to be 2, but we use the oriented Grassmannian everywhere, because these are meant to be oriented surfaces. Okay, so this is nothing. I mean, this is nothing but notation for the following. You take the n-fold loop space of the Thom space of the complement of the tautological bundle. I guess that should be 2. Over the Grassmannian of oriented 2 planes in Rn. Okay. Again, when I was defining this space here, I just talked about manifolds abstractly. One can make an equally good definition for manifolds with orientation and for manifolds with all sorts of other structures on them as well. Here you have to do the oriented version. If you do that, then you have a map, just as before. Oh, there's another small thing. So I should have said here as well. This space, as you well know, what are the path components of this space? The path components are the maps from the sphere to itself, and there's the integers, many of those, given by the degree. On the other hand, this space is always connected. So what I said here is not strictly speaking true, because they have different sets of path components. So one ought to just restrict here that one lands in the path component of the degree 0 maps. Similarly here, that's what this little decoration is. You take a particular path component. Now one takes, exactly the same way, a limit here over making the surface bigger. Just like here we added points to a 0 manifold to make it a more complicated 0 manifold. Here we glue on a genus 1 surface with 2 boundaries. So we glue it along this boundary to a genus G surface with 1 boundary, and you get a genus G plus 1 surface with 1 boundary. And that's how we form this direct limit here. And the theorem has exactly the same statement. Then once you construct this map, this is a homology isomorphism. The upshot of this is that, as I said, this side is an infinite loop space. There are very good tools for calculating things about it. In particular, if one wants to know the rational cohomology of this space, That's something one can just read off once you know how to do it. And here it's not difficult to see that the rational cohomology is a polynomial algebra on certain classes kappa 1, kappa 2, where kappa I has degree 2i. And these are very well known. So more precisely, when one pulls these classes back to here, these are very well known cohomology classes, originally due to Mumford, when one thinks of this as being the usual moduli space of Riemann surfaces, and later studied by Morita, by Miller. And the Mumford conjecture was that when one takes the stable cohomology of all these moduli spaces, when you make the genus bigger and bigger, that the rational cohomology is exactly this ring. And that's an immediate consequence of this theorem and a very easy calculation of the cohomology on this side. I won't go into the calculation precisely, but once one knows the cohomology of Grassmannians and what the Thom space construction does to cohomology and what the loop space construction does, it just falls out immediately. So the result I'd like to talk about is a generalization of these two. If you like, this is something about zero-dimensional manifolds. This is something about two-dimensional manifolds. And we have a result about even-dimensional manifolds of higher dimension. Unfortunately, not of dimension 4 for the usual problems in manifold theory. So even-dimensional manifolds of dimensionally 6. And the result is actually quite general, but let me just write to you the version that is most similar to the two that I've written down here.
What about odd-dimensional manifolds?
I'll come back to that at the end if you don't mind. That's a very interesting and difficult question. We don't have a theorem in that case, and the obvious generalization is untrue, is the short answer. So our theorem is as follows. We let n be at least 3, and we write Wg, let's say, for the connect sum of G copies of Sn cross Sn minus a disk. Okay, now if one allows n to be 1, this is nothing but what I wrote over there. This is a surface of genus G with one boundary. And this is what I'm claiming is the correct generalization to other even dimensions. Then this gets a little repetitive, but it's exactly the same thing. There's a map from the limit of these, and how do we form the limit now? We form the limit by connect summing with Sn cross Sn. That's basically what we did there, or rather Sn cross Sn minus some disks maybe. And there's a comparison to something over here. Let me write it out in notation first and then say what it means. What this means is the limit, again, as n goes to infinity, of the n-fold loop space, of the Thom space. So now we do a bit of a funny thing. We take the Grassmannian of two n planes inside our capital N. And here, what did I say? Here I said we had to not just take the ordinary Grassmannian, we had to take the oriented Grassmannian. In other words, we had to take the universal cover of the ordinary Grassmannian. Here, another way of saying that is you have to take the thing closest to the Grassmannian that is simply connected. Here, we have to take the thing closest to the Grassmannian, which is n-connected. So you homotopically kill the first n homotopy groups of the Grassmannian. That's a completely functorial process. You can do that for any space. And you take that. So, well, let me come back to what that means in a second. It's a cover. It maps down to the ordinary Grassmannian. and in particular it has a bundle over it, and you take the pulled back bundle and you take the Grassmannian of that. This is a bit of a funny construction. Basically, the reason is that these manifolds are n-1 connected. So the map from the manifold to the Grassmannian that classifies its tangent bundle at least lifts to the n-1 connected cover of the Grassmannian. Just by elementary homotopy theory, there's no obstructions to doing that. Furthermore, the tangent bundle here, if you restrict it to the n skeleton, is trivial. Because on the n skeleton, this looks like a wedge of two spheres, and the spheres are parallelizable once you are stably parallelizable. So you get a bit more connectivity coming from the fact that on the middle dimensional skeleton, the tangent bundle is sort of trivial. The tangent bundle of this is only non-trivial on the very top cell, if you like. That's some reason why you might expect this, but.
And D here is 2n?
Sorry, yes. Yes, thank you. And the statement is the same. Then this is a homology equivalence. So there's a far more general theorem. For example, you can take a direct limit. You don't have to glue on the same thing every time. You can glue on lots of different things as long as they basically have similar properties to this. Whatever. I mean, I haven't told you what properties they need to have, but they need to have similar connectivity properties. And then you get a different answer over there. So this is the basic and the easiest to state version of our results. Let me tell you what this means for the cohomology of these spaces. So the point of this is that I've told you we can calculate this side. So let me tell you what that is. So to do so, I need to describe first some characteristic classes. I mean, the cohomology of this side is going to be characteristic classes of bundles of manifolds. So I need to describe some characteristic classes for you. So let E to B, pi maybe, be a fiber bundle, smooth, d-dimensional fiber bundle. How can I get some sort of naturally defined characteristic class? Well,
Let's say d-dimensional, what do you mean?
The fibers, yeah,
Fibers.
right, yeah. D-dimensional fiber bundle. How can we, right, so we know about characteristic classes for vector bundles. And let's take that as a given. So maybe, so if C in the cohomology of B, let's say SO D, is a characteristic class of vector bundles, how can we get a characteristic class of manifold bundles? Well, one can make the following construction. Let me call it kappa C of E. We take the characteristic class, and we need, if we want to evaluate it, we need some d-dimensional vector bundle to evaluate it on. And we evaluate it on the so-called vertical tangent bundle of E, right? If you allow B to be a manifold, say, then a fiber bundle is in particular a submersion, and the vertical tangent bundle is nothing but the kernel of the differential of this map. So it's the tangent vectors on V which project down to the zero vector in the base. In fact, one can make sense of that even if the base isn't a manifold. But so that gives us a cohomology class on E, because this bundle is on E. And then we can fiber integrate it down to the base using pi. And that lives in the cohomology of the base. It lives in whatever degree the characteristic class C was in, but then the fiber integration moves it down d degrees. Okay? So given any characteristic class of bundles, of vector bundles, sorry, we get a characteristic class of manifold bundles by doing this construction. So now the corollary to this theorem that I like to say is, let's see, so let so I want to define B inside the cohomology of BSO to n, be a certain set of monomials in the generators there. If you don't remember, let me just remind you what the cohomology rationally of BSO to n is. It's a polynomial algebra on, well, we have the Euler class of the bundle in degree 2n. We have the Pontryagin classes, P1 up to Pn minus 1. And I guess we also have the nth Pontryagin class. But the nth Pontryagin class is the square of the Euler class. So for generators, that we don't really need that. So let B inside there be the set of monomials in the Euler class, and then the Pontryagin class is reading downwards from the top one to P ceiling of n over 4. Okay, so we don't use the bottom Pontryagin classes. We use the Euler class and we use the top Pontryagin classes up to the ceiling of n over 4th one. And also, you see, if here you take a characteristic class of degree less than d, when you fiber integrate it, it's in negative degree, it's automatically 0. So we don't want to take those. So let's say, take things of total degree, at least 2n. Then one can form the polynomial algebra in these characteristic classes indexed over these monomials, so you don't take all possible things. And there's a map from that to, well, so for each g we can evaluate this and get an element in the cohomology of MWG. And then these are natural enough that it extends and gives one in the limit, in the inverse limit now, I guess, of the cohomologies of these. And this is an isomorphism. So that gives a complete description of the rational cohomology of these spaces once you allow yourself to stabilize by connect summing with these Sn cross Sns. It says, firstly, something that's not very obvious, that these classes are non-zero. That's actually already a theorem in itself. That, I mean, you know, I've defined them, but they could always be 0. This says they're not, apart from the ones that are not included here, which are. And furthermore, that there's no more cohomology. So unstably, at any particular stage, there probably is more cohomology. That's certainly true for surfaces. But stably, there's no more. I'm not sure, how am I doing for time?
Exactly on time.
Exactly on time? Okay, maybe I'll. I just.
So it's a touch late, which has gone. The odd dimensional case.
Right, okay. So I can't say anything with content about the odd dimensional case, unfortunately. Let me just say one consequence of this, which I think is a little interesting, and maybe Andrew will appreciate. So, the later in the talk, surely the narrower the audience is supposed to become. So, the Euler class, I mean, you don't really need a thing to be a manifold to have an Euler class. You have Euler class in great generality, right? I mean, if it was a topological manifold, certainly it would have an Euler class. In fact, if it was a Poincare duality space, it already has an Euler class, basically. That's not strictly true, I guess.
I mean, if it's a Poincare duality which has a tangent.
Yeah, okay. But in any case, all I want to say is if it's a topological manifold, it certainly has an Euler class. And due to a rather deep theorem of Novikov, if it's a topological manifold, it also has Pontryagin classes. So all of these things can be defined for bundles of topological manifolds. In particular, where shall I? In particular, they can be defined on the classifying space of the homeomorphism group of these WGs. So this factors through the exact same thing, but I mean, I said that this is basically the same as the classifying space of the diffeomorphism group. It factors through the cohomology of the classifying space of the homeomorphism group of WG, again with rational coefficients. This is just algebraic. I'm not saying that the map geometrically factors through. I'm just saying that the statement I've written down here factors through. So, what does that mean? In particular, it means that the map from the diffeomorphism group to the homeomorphism group gets you all the cohomology that you want, or all the cohomology that there is, i.e. that there's a surjection from the cohomology of the homeomorphism group rationally, yes. There's a, right, exactly, this statement. And that is something that, of course, Besno, I mean, one can ask this question without making reference to all these scanning maps and this geometric side of the story. But I don't know that there is, could there possibly be some a priori reason that this should be true? For example, is this true if I don't take limits? That I don't know. So can all characteristic classes, rational characteristic classes of smooth manifolds be defined on the underlying topological thing? I think that's unlikely.
I mean, Michael Weiss's project was 15 years, like
yes.
Unstable Copenhagen classes.
Right.
I don't know.
So, right.
What was he said?
Well, so for topological bundles, firstly, a priori there may be higher Pontryagin classes, and it may not be true that the nth one is the square of the Euler class.
Exactly.
Those two facts hold for vector bundles, but even though you can define these for topological bundles, that those are not known to hold for topological bundles. And that could well account for the kernel here. That there's things you can define. If the thing happens to be smooth, then they're automatically zero. But the question of whether everything that can be defined on smooth things in fact lifts in some maybe non-canonical way to topological manifolds is, I have no idea about. But yeah, I mean, it's a consequence that stably it's true. And that's maybe I'll leave you with the question. Okay, thank you very much.
Apart from the odd question, other question. I think you can answer the odd question. What can you say about
the odd dimensional? Well.
And I know it's content free. It's all right.
No, I mean I can tell you what's
switch the camera.
I can tell you what's how it fails to be true. That the obvious. I mean, everything that I define, you can define the maps in the odd dimensional case. And this is a theorem due to Johannes Ebert. He showed that if you have a bundle of odd dimensional manifolds, let's do the simplicity 3-dimensional manifolds. It doesn't really matter. You get a map to, in exactly the same way, this infinite loop space type thing over here. Let me write it like this. It's the thing defined using the classifying space of SO to n+1. Maybe this is an oriented manifold, and we take orientation preserving diffeomorphisms. Now here, you see, if you take C to be one of the Hirzebruch L classes for some n. Okay, so this is some particular polynomial in the Pontryagin classes. Then he showed that kappa C for that C over here is 0, maybe rationally. Okay, so for any bundle of odd dimensional manifolds, you take the Hirzebruch L class of the vertical tangent bundle, and you fiber integrate it, and that's always 0. And he proved that by identifying it with the index of a certain operator, and then seeing that in fact the operator he could trivialize in some geometric way. On the other hand, I said these classes can be defined here. So they live in the cohomology of this, and here they are not zero. But it pulls back to this zero class here. Okay, so so there's no hope that the theorem is true, right? We've just found something in the kernel, so it's not an isomorphism. On the other hand, the only things we know this to fail for is these things coming from the L class. So there's sort of a I don't know if you would call it an obvious guess as to what the correct statement might be, which is not this infinite loop space. It's a slight variant of it. And this, I appreciate that this is a little technical, but let me just, it's not very long. So somehow this MTSO2 thing is some unstable version of the usual spectrum that classifies cobordism theory. In particular, you can forget that it's unstable, and you go to the ordinary thing that classifies cobordism theory, which is something like maybe it's called that in homotopy theory. So this is just forgetting that it's unstable. Now there's a universal place where things like the Hirzebruch L class should come from, which Andrew basically maybe, well, has done a lot of work on, let me say it that way, perhaps invented, I don't know. Okay. But in any case, there's a map to some sort of thing, maybe it should be called something like that, maybe. And all of the L classes come from here. And somehow rationally that's all that's left here. Rationally this is just the universal thing that...
I should say just a space made from symmetric form. Symmetric matrices of integers.
Right. Okay. So okay. So the best thing you might hope for is that the fiber of this map is the best approximation to an odd-dimensional diffeomorphism group. But that would mean, I mean, this discussion in rational cohomology basically means that this map in rational cohomology is zero. That's not enough to lift the map here. You'd need some geometric reason why this composition is actually null homotopic. And this composition is it's a characteristic class, but in this exotic, very exotic cohomology theory, not in ordinary cohomology. And one would need some geometric reason why for odd-dimensional manifolds that's always zero.
Does it help at the odd-dimensional manifolds twisted level?
This is the diffeomorphism group.
Yeah,
so
so
if things are canonical, they don't really help here. It has to. If that thing would be great if they were somehow canonically constructed in this way.
Interesting to study.
Yeah.
Class of a twisted double.
With the splitting as part of the data. Yeah, absolutely. Right. Maybe I'll stop there. Anyway, this is maybe the next best guess, but there's no real reason apart from the fact that it's the minimal place where the counterexample fails.